All right, what is up, everyone? Welcome. Today, we are cracking open NMK42003 Instrumentation. And I want you to think of this like a big tech unboxing. But, instead of the latest gadget, we are getting hands-on with the tiny, brilliant components that make all of that tech possible in the first place. Our lead engineer for this deep dive is Dr. Mohd Zamri, so let's get right into it.
So just look at these. It all starts right here. From the little gyroscope in your phone that knows exactly when you tilt it, to the sensor in your car that starts beeping when you get a little too close to the curb, it all begins with these little guys. Seriously, they are the nervous system of our entire modern world.
Okay, so let's start with the quick start guide. The first impressions. Before we dive into all the heavy specs and the numbers, we gotta understand the absolute basics of how our devices actually talk to the world around them.
And the core idea, the big one, is the transducer. A transducer is basically just a translator. It takes something physical, like pressure or heat or sound, and it converts it into a language that our electronics can understand, which is, of course, an electrical signal. And, as we're about to see, this translation can go both ways.
This is the perfect example of that two-way street. When you speak, your voice creates sound waves. That's a physical thing. A microphone, which is our first transducer, grabs those waves and turns them into an electrical signal. Then that signal gets processed, sent over to a speaker, our second transducer, which turns that electrical signal back into physical sound waves. It's a perfect, elegant loop.
So this brings us to a really crucial point. You have to know the difference between sensing and doing. A sensor is the input. Think of it as the eyes and ears of a system. It just detects that something happened. But an actuator? That's the output. That's the hands. It takes the signal from the sensor and then performs a physical action, like spinning a motor, flipping on a light, or, well, making a sound.
Now, these sensors, they pretty much come in two main flavors. You've got passive sensors, which are kind of like a light switch. They need some external power flowing through them to do their job. And then you have active sensors, which are more like tiny generators. The physical change they're detecting actually creates its own little electrical pulse, all on its own.
Okay, basics are down. Now we get to the fun part, the deep dive. Let's say you are buying a sensor for a really critical project. How would you actually know if it's any good? Well, we're going to approach this just like reading the spec sheet on a really high-end piece of tech.
And these 6 things right here, this is everything. These parameters define the performance, the quality, and honestly, the trustworthiness of any sensor you're ever going to use. So let's break them down one by one.
First up is linearity. And this is so important because it means the sensor's response is predictable, right? Think about a dimmer switch for a light. As you turn the knob up, you want the light to get brighter, smoothly, proportionally. You don't want it to flicker or jump around. A nice straight line response means the math is easy and you can trust the readings without a bunch of complicated fixes.
Next up, repeatability. And folks, this one is completely non-negotiable. Imagine stepping on a bathroom scale and it gives you a different weight every single time, even though you haven't changed. It's useless, right? Well, it's the same thing here. A sensor must give you the exact same output for the exact same input over and over and over again. If it can't do that, your data is just noise.
All right, let's talk dynamic response. This is all about one thing, speed. Can your sensor actually keep up? Think about it like input lag when you're playing a video game. If your controller is slow to respond, you'll turn the wheel, but the car on the screen won't react for another second, and you're going to crash. A sensor in a fast-moving system needs that same instant, faithful reaction.
Now, what about signal quality? Look, the world is filled with electrical noise. It's everywhere. Motors, power lines, you name it. A great sensor is one that produces a signal that is so clean and so strong that it rises way above all that background noise. A weak, noisy signal? That's like trying to have a conversation at a loud concert. You can't be sure you're really hearing the right thing.
Reliability and stability. This is the long game. You have to be confident that the sensor you install today is going to give you the same accurate readings a year from now, maybe even 5 years from now. If its performance starts to drift and change over time, well, your whole system just became untrustworthy.
And finally, we have hysteresis. Now, this one's a little subtle, but it's so important. Think of it as a memory effect. A good sensor should have 0 hysteresis. That means the reading at, say, 30 degrees Celsius should be exactly the same whether the temperature is rising up to 30 degrees or falling down to 30 degrees. The path you took to get to the measurement shouldn't change the measurement itself.
So now we know what a great sensor looks like on paper. Let's actually put it into practice. We are now moving from theory to real-world application.
So I want you to imagine this. You're a newly hired engineer. Your very first big task is to pick the right sensor for a critical system. If you get it right, hey, the project's a huge success. But if you get it wrong, it's going to be a very, very bad day at the office. So, how do you make the right call like a pro?
You use a checklist, a professional one. First, what are we even sensing? Temperature, pressure, light? Next, what's the operating principle? How does this thing actually work? Then, accuracy. How close to the absolute truth do we need to be? What about resolution and range? What's the smallest change we need to see, and what's the maximum value it has to handle? Then you got to think about power consumption. This is a huge deal for battery-powered devices. A power-hungry sensor can be a total project killer. Of course, there's always cost, balancing performance with the budget. And finally, the big one, environmental conditions. Will this thing survive the heat, the humidity, the vibrations of where it's actually going to live? Making the right choice means you have to weigh all of these factors every single time.
Okay, so you've done it. You've gone through the checklist, you chose the perfect sensor, you're getting clean, reliable data. But that's only half the story. Now you actually have to do something with all that great information.
And this is exactly where the actuators come in. They take that electrical signal from your sensor and they complete the loop. Your temperature sensor detects it's getting too hot, so an actuator, like a relay, kicks on a fan. Your light sensor detects it's gotten dark, so an actuator, an LED, turns on. See? The sensor is the trigger, the actuator is the action.
And that really brings us to the most important takeaway of this whole thing. See, Dr. Zamri isn't just teaching you how to memorize a spec sheet so you can pass a test. He is teaching you a professional mindset. The goal isn't just to make something that works once in a lab. The real goal is to understand these principles so deeply that you can go out and build robust, reliable systems that people can actually depend on. That is the real work of an engineer. Thanks for tuning in.